Problem is from June 2012. What they're asking is to calculate the coupling constant, and what they've given the chemical shift values of the doublet. So suppose I have a doublet like this. So this is a doublet and they've given the chemical shift of these doublets. So we know that the chemical shift of the particular proton will lie at the center of the multiplet. So center is here, but they're given the values for the positioning of these doublets. So it is 2.35 here and here it is 2.38, and they're asking for the coupling constant. So we know that the distance between the adjacent lines of the multiplet, so this distance is known as coupling constant. So this coupling constant is given in terms of hertz. So now, but here we have only the chemical shift values. So the chemical shift value is 2.35, 2.38. So subtract them. So the difference between the chemical shift value comes around 0.03 ppm. So it is in parts per million. But we know that coupling constant is always asked in hertz. So what should you do? Just multiply the resulting ppm value with the operating frequency of the instrument, 400 megahertz. So this is in ppm 10 power minus 6, and megahertz will be 10 power 6 hertz. So this 10 power 6 and this will get cancelled. So we'll be getting 12 hertz. So the answer is option D, 12 hertz. Very simple. So if they're given in hertz, just subtract the value. On subtraction, you'll get the coupling constant value you'll get. But since here the difference we are getting in ppm, if you get in ppm, what you do? You multiply by the operating frequency in megahertz, and you'll get the coupling constant in hertz. Very simple. Or what you can do is you can multiply this 2.38 into a 400, 2.35 into 400, get the value in hertz, and then subtract them. That is very tedious. I've got very simple without doing much multiplication step. So the next problem is December 2011. They're given a molecule with AX3 type. Now what they're saying is that the doublet comes around 2.1 and 2.3, and the X comes around. So if I say this is X spectrum, so 4.1, 4.3, 4.5, and 4.7. And the doublet is coming around 2.1 and 2.3. This is measured in TMS as the internal reference, and they're asking for the chemical shift of A and X protons and the coupling constant in Hertz. So we know that this is for the X proton and this is for the A proton. And we should know that the center of the multiplet lies at its chemical shift. So 2.3 minus 2.1 will be zero point 0.2. So the median or the average comes around 2.2. So 2.2 is the chemical shift, the midpoint between 2.1 and 2.3. So 2.2 is the midpoint between 2.1 and 2.3. Therefore, that is the chemical shift of X proton. So A is 4.4, X is 2.2. So I have 4.4, 2.2. So this is wrong, this is wrong, this is wrong. Very easy, is it not? So just by knowing the midpoint of the multiplets, I've got the chemical shift. Now let us just solve for the J value. So the difference between the lines of the multiplet, 0.2 ppm. Okay, now I want in hertz. So what you should do? 0.2 into operating frequency, which is given as 100 megahertz. So it comes as 20 hertz. Okay. So the answer is 4.4, 2.2, and 20. Option A is the right answer. The next is GATE 2017 question. What they're asking is the C13 NMR spectrum of acetone D6 has a signal of 30 ppm as a septet, and they're asking for the intensity ratio. So if we know the Pascal's triangle, it becomes very easy. So as you would have seen in the Pascal's triangle, we have the midpoint 1, then you have 1 and 1. This becomes 1, 2 and 1, then 1, 3, 3, 1, then goes 1, 4, 6, 4, 1, then goes 1, 5, 10, 10, 5, 1. So they've asked for septet, so it is 1, 6, 15, 20, 15, then 6 followed by 1. So 1, 6, 15, 20, 15, 6, 1. So the answer is option E. Very simple. So here it is. This is acetone, and they are talking about CD3, C double bond O, CD3. Is it not? So deuterium is D, which is I equal to 1. So for deuterium, I is equal to 1. Therefore, 2Ni plus 1 formula for splitting. So I'll be having 2 into how many neighboring protons per carbon? You have 3 deuterium. So 3 into 1 plus 1. So you'll be having 6 plus 1, which is equal to 7. So generally we say n plus 1 rule. So that is nothing but 2 into Ni plus 1. So the for an proton, the I value is half. So it simplifies to n plus 1 rule. But since for deuterium I is not equal to 1, we have to write this formula and find the answer. So that is why the CD3 of the acetone gives you a septet, and the signal intensity is 1 is to 6 is to 15 is to 20 is to 15, 6 is to 1. Okay. A very interesting problem, December 2016. So they are saying that the proton spectrum of organic compound is recorded on a 500 megahertz instrument, and they get it quartered with line position at 1759, 1753, 1747, 1741. They're asking for the coupling constant and the chemical shift. So this is the quartet. Let me draw the quartet first. Okay, so they've given in hertz. The hertz value are 1741, 1747, 1753, and 1759. Okay, and what do we know already? The distance between the adjacent line of the multiplex is the coupling constant. Okay, so it is 1747 minus 1741, which comes around 6. And since the values are given in hertz, just subtracting will give me the coupling constant value. So the coupling constant value is here 6. So 6 is the coupling constant value. So option 2 is wrong, option 4 is wrong. And now the midpoint of this particular line is the chemical shift in delta. Get 1750. Now this is the value in hertz. How to get in ppm? Just divide 1750 divided by the instrument megahertz. Okay, and we will get the answer. So it comes around 3.5. So the answer is 3.5 and 6 hertz. December 2016 problem, they're saying that in a 200 megahertz spectrometer, a molecule shows two doublets. So you have two doublets. You have two doublets. And these doublets are separated by 2 ppm. So they have given a separation of the doublets. And the coupling constant. So this coupling constant, the distance between the lines of the multiplets given as 10 hertz. The separation between these two signals and the coupling constant is 600 megahertz they are asking. Okay, so they're asking what will be the coupling constant and the separation between these two signals in a higher version of the instrument, 600 megahertz. Just keep in mind that the coupling constant 10 hertz will remain constant whatever be the instrument you are using. Okay, so the first option and the second option is gone. So you have third and fourth option. Now you have the delta value which is 2. This will also remain constant. 2 ppm will remain constant. So the separation between the doublets will be the separation between the doublets 2 ppm, that will remain constant. So 2 is equal to, so in the previous case it is 200. So the instrumental frequency is 200, and the separation between the lines is 2 ppm. So 2 into 200. So the separation between the lines is 2 ppm. How to convert into hertz? Multiply the 2 by 200, you get 400 hertz. So what we have in numerator is 400 hertz. So when I subtract, I get 2. So now they are asking what will be the separation in hertz when I go for a 600 megahertz instrument. So this 2 remains constant. I have 600. So in order to get 2, what should be done in the numerator? It should be 1200. Very simple. So the answer is option 4, 1210 hertz. So when I divide this 1200 by 600, I'll be getting 2. So the 2 I'll be remaining constant. So in order to have the 2, the separation between the lines doublet should be 1200 hertz in a 600 megahertz instrument. That is why we say that when we go from a 100 megahertz instrument to a higher version of the instrument, the lines get separated, the doublets or multiplets get separated, and you get a clear spectrum. So usually, if you in 100 megahertz, you are getting a second order spectrum very coalesced, like all the peaks are overlapping with each other. When you go for a higher version of instrument, the peaks will get separated because the distance between them is increasing. So you'll get a clear spectrum. It goes from a second order spectrum to a first order spectrum. So this is December 2017 question. Here they are asking for the multiplicity of DMSO D6, so deuterated dimethyl sulfoxide. Okay, so the carbon is attached to 3 deuterium, and we know that deuterium I value is equal to 1. So already we have seen similar kind in acetone, so 2Ni plus 1, so it comes into 2 into number of deuterium is 3, I value is 1, and plus 1. So 6 plus 1, it comes to be 7. 7 is septet. So answer is option 4. December 2017 problem, they're asking for the organic compound that displays the following data. So it is given 7.38 doublet, 7.25 doublet. I have told you so many times, whenever you have this doublet and doublet situation, so if I have X and Y, so you have hydrogen, 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 hydrogen here. So these two hydrogens will be A proton and these two hydrogens will be B proton. A has one neighbor, 1 plus 1. A will be a doublet. B is also having one neighbor, therefore 1 plus 1. B will be also a doublet. So whenever you have this doublet doublet pattern, you should be very clear that it should be a para disubstituted. Okay, so it's a disubstituted first and it is para disubstituted. So option 4 is readily we can remove it. And you have only one signal for the proton, only one signal. This will give me two signals for proton. Third molecule give me one proton signal here and one proton signal here and this particular proton signal here. So I have only one signal in the alkane region. So here I'll be having three different alkane regions proton. So 3 is also wrong. So answer is option 1. So option 1 you have this all the three CH3, there are no other alkyl group here, so all these three CH3 will come around 1.29. So answer is option 1. A June 2017 problem, they're asking for the correct structure and then giving you the particular data. So here you have 3.59 singlet and you have 3.32 triplet and 2.25 triplet. Two hydrogen, two hydrogen, three hydrogen, and you have a 1.85 and 1.75 multiplet with two hydrogen, and again 1.73 and 1.62 multi two hydrogen. So you have only one particular set of proton which are three hydrogen. So if I look into this particular problem, I have here three hydrogen. So here I have three hydrogen. So these two molecules has a CH2, CH3. Here you have a CH3. Here you have a CH3. So here I have two CH3. So I have got only one particular set of hydrogens, which are three hydrogens. All the other are two hydrogens. Look here, all the other are two hydrogens. So this particular fourth option is a wrong option because it has two CH3 protons. So it is straight away we can say it's a wrong option. Since I don't have this triplet quartet combination, I don't have this ethyl group, so this is straight away ruled out. Now this particular CH2 will be coming around 2.3, not more than that, because it is attached to a C double bond O. So here this can come more than 3.6. So can be around 3.6. It should be more than that. So only this particular molecule matches the value of this 3 hydrogen. So 2 is also wrong. See, I'm not gone into further just by taking only one particular set of hydrogens, I will be able to solve the problem. Now you can see you have triplet 2 hydrogen, so you have 3.32. So this will be triplet 3 2 hydrogen. Now this will be also a triplet 2 hydrogen and these two will give you a multiplet because you have protons on either side, they'll give you a multiplet. So answer is option 3. June 2016 problem, they're asking you to find the correct structure And here they are given the IR value as 1690. 1690 cannot be ester because ester will come around 1750. If it is having a conjugation, it can come around 1720 or 1715, but not less than that. So option 2 is ruled out, option 4 is ruled out based on the IR value. Okay, and now they're given you have the doublet and doublet pattern. So when I have doublet and doublet pattern, I can rule out this meta option. So option 1 is the answer. Very simple, is it not? Okay, let us just go through the problem and find whether it's right or wrong. So I have a 3.8 singlet 3 hydrogen, 2.5 singlet 3 hydrogens. So I have two methyl protons which are coming at 2.5 and 3.8. So this will come around 2.5 3 hydrogens and this will come around 3.8 3 hydrogens. Is it not? And you have a value of 6.9 and 7.8. One side you have a shielding, the other side you have a d shielding. So this will be a plus R group and this is minus R group. So these protons are d shielded, they'll come around 7.8, and these protons are shielded, they'll come around 6.9. See, very simple. By IR value, I'm able to do this problem. So with the help of IR, I'm easily able to crack this problem. Is it not so? An organic compound shows spectral data like this, and they've given the four options. They're asking you to find the correct answer. See, so in mass, they're given M peak and M plus 2 peak. So M and M plus 2. So they are known as isotopic peaks. And you can see in the oxygen, the abundance of O16 and O18 is just 100 and zero point 0.2, whereas in sulfate it's coming around 100 and 4.4. So as you can look into the problem, they are given 104.4, nearly 4, 4.4, 4.8, 4.9. So only here this problem it is ranging with the sulfur abundance. Okay. So you should have a sulfur in the molecule. So option 1 is gone, option 3 is gone. So I'll be dealing with mass spectrometry. There we will discuss all this in detail. So now you have the carbon NMR, you have 190. So if I have a ketone, it should go beyond 200. Therefore, the option is option 2. Very simple. So answer is option 2. 2014, they are asking for the correct structure and then given you the datas here. So they have given 1.853 hydrogen doublet and 3.83 hydrogen singlet, 5.01 hydrogen which is exchangeable, and you have a 6.0 doublet of quartet, 6.28 one hydrogen doublet, 6.75 one hydrogen doublet, 6.8 one hydrogen singlet, 6.9 one hydrogen doublet. So you have 6.75 one hydrogen doublet, and this both are coupling partners. Okay, they have got 8 hertz and 8 hertz. They are the coupling partners, so they should be the neighbors. Okay, so they are aromatic protons. And now you can see here you have a 18 hertz, 18 hertz. So 6.0 one hydrogen doublet of quartet 18 hertz and 6.28 one hydrogen doublet 18 hertz. So 18 hertz means it should be a alkene. So 4 to 6 is alkene, and alkene should be a trans alkene. So only the trans protons will undergo coupling with high J value. Option 2 is gone. Now you have option 1, 3 and 4 in hand. 6.8 one hydrogen singlet. So singlet means it should be like a meta. So singlet means you have one hydrogen which does not have a neighboring partner. So something like this here. But here it is not possible. So here you will be having doublet, triplet, doublet. So option 3 is gone. So since you need a singlet, you can have option 1 and 2, or it can be option 4. But option 3 is gone. So already we have seen that option 2 is wrong. Option 3 is now gone wrong. So now we have answer which could be option 1 and 4. Now look into the problem. They've given 1.853 hydrogen doublet and 3.83 hydrogen singlet. So 3.83 hydrogen singlet. So I can have this methyl, this methyl. So I have a methyl here, I have a methyl here. This methyl has a neighboring one hydrogen, therefore it will be a doublet. So this methyl will remain as a singlet. And this singlet comes around 3.8. Whereas a methyl attached to an alkene system will come around 1.7 something, or it can go to 2.0 something, and this will be also 2.3 something. So here I have 2 methyl, 3 hydrogen, 2 methyl, which will be around 2.3 or 1.7 or 2, not more than that. So option is all 4 is also wrong. So option 2 gone, option 3 gone, option 4 gone. So option 1 is the right answer. Okay, so this omethoxy comes around 3.8. This methyl 3 hydrogen doublet comes around 1.85. And you have these hydrogens, they are coming around 18 hertz coupling. Okay, so they're coming out 6 and 6.28. So these two are alkene hydrogen. This alkene hydrogen is one neighboring hydrogen, so 1 plus 1, this will come as a doublet. Whereas this has two neighboring hydrogens. So this two, methyl and hydrogen, they are far different in their chemical shift values. So this hydrogen will be split twice by this methyl and by this hydrogen. Okay, so that is why you have DQ, doublet of quartet, DQ. So keep that in mind. Then you have 5.0, the exchangeable OH, and this you have this OMe which comes around 3.8, and you have this methyl which comes around 1.85. This aromatic proton comes into a singlet, and these are the aromatic protons which comes as doublet. So doublet and doublet. Okay, so the answer is option 1. On 16, they're asking the proton NMR spectrum of a mixture of benzene and acetonitrile shows two singlets of equal integration, and the molar ratio of benzene and acetonitrile they're asking for. Okay, so benzene is C6H6, acetonitrile is CH3CN, CH3CN. I have here 3 hydrogen, here I have 6 hydrogen. Two singlets of equal integration, therefore it is 1 is to 1. So now what is the formula? The formula is the molar ratio, of benzene to acetonitrile they're asking. So the integration of benzene, intensity of integration for benzene divided by total number of benzene hydrogen divided by the integration of acetonitrile, intensity of integration of acetonitrile divided by total number of hydrogen in acetonitrile. So the molar ratio is the integration or the intensity of integration of the benzene by total number of benzene protons and integration of the acetonitrile by total number of acetonitrile protons. So it is 1 by 6 into 3 by 1. So it is 1 by 2. So the answer is 1 is to 2. Very easy. Option 3. Hope you have understood this video very clearly. If you have any doubts, you can post that in the comment section. I'll be solving the problems related to complete NMR, which have dealt from the part 1 till part 4 in the next video. Kindly go through all the videos and get to know the NMR spectroscopy problem solving in detail. If you want to listen to such videos, kindly like, share, and subscribe. Thank you.